So, question number 1 and 2 were all about properties of exponents. I mean, you really couldn't do this problem unless you know your properties. To refresh our memories, the main ones that we typically use are the product property, which says if you multiply like bases, you can condense them together by adding the exponents. We have the quotient property, or the division property, which says the exact opposite. If you divide like bases, you can subtract the exponents. The power property says if you have an exponential expression and you raise it to another exponent, you can just go ahead and multiply the two exponents together. And the last of the more common ones we typically use is the negative exponent property, which says if you have a negative exponent, all that negative does is it reciprocates the base. So these problems are just applying these properties one at a time in a correct manner. Now, there is no one singular way to do this. There are a lot of different avenues you can take. So the solution I'm posing is just my take on it. You can certainly solve it in a different order. The first thing I notice is I have an exponent outside a set of parentheses, so I'm going to distribute that exponent in. That's the power property. Anything that I do not highlight, I'm just going to copy down again. So this equals h to the negative 5, j to the negative 4, times h to the 6, k to the 12. That's distributing the 3 there. And then just copy down the rest. Now what I like to do is I like to clean up the numerator a bit. Do notice that the numerator, everything's multiplying each other, so it's going to be the product property. And also note that these properties only work if the bases are the same. So don't mix and match the letters. If the letters are different, leave them separated. But if the letters are the same, you can go ahead and apply the property. So the property says if you multiply like bases, you add them. So negative 5 plus 6 is just a 1. So you have h to the 1 power, and then just copy everything else down. Now, some people like to do the negative exponent rule here. I just go ahead and just do the division rule, the quotient rule. And again, you only apply the properties to the like bases, so don't mix and match the letters. Just focus on the letters that are the same. So the H's go with H's, J's with J's, K's with K's. Now, if you look at the quotient rule right here, notice it's a minus b. A is the numerator, b is the denominator exponent. And you can certainly do that. What I'd like to do instead of top minus bottom is I'd like to do big minus small, the bigger exponent minus the smaller exponent. You just have to remember to put your answer wherever the bigger exponent was. So for example, in the h's case, I have exponent of 1 and 5. I'm going to do 5 minus 1, which is 4, h to the 4. But I'm going to put my answer, h to the 4th, in the denominator because that's where the bigger exponent was. Moving on to the j's, the bigger exponent is the 5, and the smaller exponent is the negative 4. So 5 minus the negative 4 is 9. And I'm going to put the answer in the denominator, j to the 9, because that's where the bigger exponent was. And then lastly for the k's, the bigger exponent is 12, minus the 2 gives me a 10. I'm going to put that answer in the numerator because that's where the bigger exponent was. That is the simplified form for number 1. Number 2 is the same concept, properties of exponents. The only difference is the exponents, some of them are fractions. And I hate to say it, but we can't avoid it. At this level of the game, you have to be confident, you have to be proficient with fractions. And honestly, if you're not, just use a calculator. So nothing new here in terms of ideas, you just have to be comfortable with fractions. So again, the first thing I notice is I see an exponent outside of parentheses. So that tells me to distribute the exponent of 2 into the exponents. So that gives me m to the 3 over 2, p to the 10 thirds, q to the 8 thirds, and then just copy down the rest. M negative 1, p negative a third, q negative 2 thirds, times q p to the 4. Next, what I'm going to do is I'm going to clean up the denominator because I see multiple variables that are the same. I see a p here and a p here. I see a q here and a q here. And they're all timesing each other. So when you multiply like bases, you add the exponents. Again, anything I do not highlight, I'm just going to copy down because I'm not doing anything to them. So adding the exponents, so add negative 1/3 to a 4, so negative 1/3 plus 4 is going to be negative 1/3 plus 12/3 is 11/3. Move on to the q's. I have negative 2/3 plus 1 is negative 2/3 plus 3/3, which is 1/3. So that's q to the 1/3. Now I can go ahead and use the division rule with the like bases. So I know that 3/2 is bigger than 1, so I'll go ahead 3/2 minus a negative 1. That gives you 5/2, and since 3/2 is bigger on top, that's where my answer goes, m to the 3/2. For the p's, 11/3 is bigger than 10/3, so my answer of 1/3 should go in the denominator. And for the q, 8/3 is bigger than 1/3, so the answer of 7/3 should go in the numerator. So that is the simplified form for number 2. Number 3 is a rationalizing. Specifically, it asks you to rationalize the denominator. Now, the idea most of the time when you rationalize is to get rid of the radical. And we're just simply using the idea that radicals and exponents are opposites of each other. If I want to get rid of a square root, I need to use an exponent of 2. If I want to get rid of a cube root, I need to use an exponent of 3. If I want to get rid of a fourth root, exponent of 4, so on and so forth. So in this case here, if I ask you to rationalize, it is this piece here that I'm asking you to take care of. So it's a square root, so I need a square. By definition, squaring something means multiply by itself 2 times. So I already got one radical 8. All I need to do is multiply by another radical 8. But of course, what you do to the denominator, you go ahead and multiply to the numerator as well. So just go ahead and distribute. That's 8 rad 8 plus rad 16 all over. Now the whole point of rationalizing this part here is when you're multiplying a radical by itself, it gets rid of the square root, so you're left with an 8. So in the denominator, it's just 2 times a regular 8, which gives me 16. Now the instruction did say simplify as much as possible, so I got to simplify all these radicals. I hope it doesn't take a lot of thinking to simplify radical 8. We should know that 8 is the same thing as 4 times 2, so rad 4 is just 2. So rad 8 is 2 rad 2's. And of course, radical 16 is just a regular 4. Now do note that the 2 rad 2 here is just the radical 8. I still have the 8 on the outside. So it's 8 parentheses 2 rad 2's plus 4 all over 16, which is 16 rad 2 plus 4 over 16. Now, when it comes time to simplify, if you are simplifying a fraction that has multiple pieces and radicals, you have to look at all of the non-radical pieces. So things are simplifiable if you can reduce every single non-radical expression. In this case, we can divide everything by 4. So that gives us 4 rad 2 plus 1 all over 4. That should be the simplified form for number 3. For number 4, same concept, except we're dealing with the cube root, or excuse me, a fourth root instead of a square root. So we need an exponent of 4. So notice how inside the radical there's only a single 3. So we have a 3. We want a 3 to the 4th. That will get rid of the fourth root. Now 3 to the 4th is just 4 3's. I hope it doesn't take a lot of thinking to know that if we have 1 3, we want 4 3's, we need 3 3's. We need 3 more 3's. So I'm going to multiply by the fourth root of 3 cubed. That means 3 more 3's. But of course, what you do to the denominator, go ahead and multiply to the numerator. So distribute, we get 2 fourth roots of 3 cubes plus the fourth root of 5 times 3 cubed, which is 5 times 27, which is what? That's 5 carried to 3, 135. 135 all over. And again, the whole point of rationalizing is that you get the exponent with the radical so they cancel out. So that just equals a regular 3. Now, when it comes time to simplification, again, it's all about simplifying the radicals and simplifying the outside numbers. 3 cubed is 27 plus 135 over 3. Try as you might. This guy you can't break down. This guy you can't break down. And if you look at all the outside numbers, 2, 1, and 3, we can't reduce anything. So guess what? This is as simplified as possible. That is your rationalized form. Number 5 is rationalizing when there's a square root and a binomial. So again, we want to get the square root to have a square with it, but because it's in a binomial, there's really only one way you can individually square terms within a binomial, and that is to exploit this pattern here, the difference of two perfect squares, because that will give you the first term squared minus the second term squared. If you were to try to square a binomial just straight up, that's going to give you this extra middle term here that we do not want. So in terms of applying a square to individual terms in the binomial, you don't want to use this pattern. You want to use the difference of perfect squares pattern. So the idea is to multiply by the conjugates of whatever it is you're trying to rationalize. Since the instruction said rationalize the denominator, we're going to multiply both the numerator and the denominator by negative 7 plus rad 2. Plus rad 2. So then you just go ahead and distribute. So that's negative 28 plus 4 rad 2 over, and you could just FOIL out the denominator, but again, the principal idea is we're exploiting this pattern, so you know the product of two conjugates is just the first term squared, so negative 7 squared is 49, minus the second term squared, radical 2 squared is just a regular 2. And then you just go ahead and clean them up by combining like terms, 47. And again, when it comes to simplifying, you want to look at all the outside numbers, but there isn't a common number we can divide out. So this is as simplified as possible. Numbers 6, 7, 8, and 9 were all about factoring. And I hate to say it, there is no formula, there's no algorithm. It's one of those things where you know how to do it or you don't know how to do it. However, I do have a process and I do have some considerations. So if a quadratic trinomial is factorable, it will be the product of two linear factors. And this is the logic. Whatever you put in the first positions has to multiply to the first term. Whatever you put in the last positions has to multiply to the last term. So since the first term is an x squared, at least this should be easy. You know it's x times x. That's the only two things that times together to give you x squares. Now for the last terms, they have to multiply to 28. So what I like to do is pairwise factor that number. Always start with 1 and itself, because 1 times anything is itself. Then move up to 2. Does 2 go into 28? Sure. 2 and 14. What about 3? No. What about 4? 4 and 7. What about 5? No. What about 6? No. What about 7? Since I've already written down 7 here, I know this is the complete list. You can stop. Next, what you want to do is look at the last symbol. So that tells you to add. So this is your logic. What pair adds to the middle number of, and in this case, the middle number is 11. Right? And I hope it doesn't take a lot of thinking to know that, hey, 4 and 7 adds to 11, so those are my numbers. But I got to put pluses and minuses on them. So what I'm thinking of is a blank 4, a blank 7, and it needs to equal the middle of negative 11. So your job is to figure out the pluses or the minuses on here to make this a true statement. And I hope it doesn't take a lot of thinking to know that negative 4 minus 7 gives you a negative 11. So those are the symbols, and that is the factored form, x minus 4 x times x minus 7. Number 7 is the same idea, except, hey, the leading coefficient is not 1, so you just have some extra thinking involved. Again, whatever I put in the first position has to times the first term. Now, since it's a 2a squared, I know the only way to multiply two integers to get to 2 is 2a and a. But everything else stays the same pretty much. The last positions here has to multiply to the last number. So let's pairwise factor 40. We have 40 here, so 1 and 40, 2 and 20, 3 doesn't work, 4 and 10 would work, 5 and 8 would work, 6 doesn't, 7 doesn't, and then we're back to 8. This last number tells me to think add, but we do have to sort of stop and change our logic a little bit. Because I know for a fact that it has to be a 2a here, we do know that when we FOIL this guy out, whatever number I put into this position will be multiplied by 2. So I have to change my thought process a bit. My thought process is now, what pair such that, ST is such that, when I multiply one number by 2, and, again, the last symbol makes me think of add, and add gets me the middle number of 21. So that's what you're thinking. Which pair do I pick such that when I multiply one of the numbers by 2 and add them together gets me 21? And there's no trick around it. I'm simply going to guess and check. Let's check the first pair. Let's multiply the 1 by 2. 1 times 2 is 2, plus 40 is not 21. Flip it around, 2 times 40 is 80. That's already way too big, so I'm not going to even bother trying. Let's try the next pair. 2 times 2 is 4, plus 20 is 24. Too much. 2 times 20 is 40, plus 2 is 42. Too much. Let's try the next pair. 2 times 4 is 8, plus 10 is 18. Nope. 2 times 10 is 20, plus 4 is 24. Nope, because I want 21. Let's try this pair. 2 times 5 is 10, plus 8 is 18. Nope. 2 times 8 is 16, plus 5 is 21. Hey, that's exactly what I wanted. More specifically, I wanted 2 times 8, which tells me the 8 has to go here, and the 5 will have to go here. So the numbers I'm working with are 2 times 8, which is 16, and the 5, and I want negative 21. And again, you just have to play with the pluses and minuses until you reach a true statement. And I hope, again, it's not that difficult to know that negative 16, negative 5 will give you negative 21. So both the signs have to be negative. That is the factored form of that quadratic. Let me just rewrite it all cleaned up. And there's no way to get better at this except with just lots and lots of practice, being able to look at the structure. Number 8, more practice of the same thing. The only difference is now the first positions here. Notice it's a 10p squared, so we have a lot of different options. Because if we break down pairwise factor 10, we get 1 and 10, 2 and 5. Those are both possibilities, and I don't know which one is the correct one. It could be 1p and 10p, or it can be 2p and 5p. You have to go through the process and check both of them. So I'm not going to show all the work. I hope you guys get the idea. You can practice it on your own. For this question, I'm just going to go straight to the answer. But if you guess and check, it turns out it's not this way. It's going to be p plus 4 and 10p minus 1. So I'm letting you guys practice this one on your own if you don't get it. Number 9, notice it's not a traditional quadratic because it's x to the 4th now, but notice the structure. This first exponent is twice as much as the middle exponent and ends in a constant number. That is classic quadratic form. To make it look like a regular quadratic, you're going to let the letter u, or whatever letter you want, equal the middle variable part, x squared. That will transform your problem into u squared plus 3u minus 18. And hopefully now it becomes factorable like a regular quadratic. 2 parentheses, u and u, two numbers that multiplies to 18 and subtracts to 3. It has to subtract to a positive 3, so it'll be a positive 6 and negative 3. However, we have to remember the original problem is not in terms of u, but in x's. So wherever you see a u, substitute an x squared. So the factored form is going to be x squared plus 6, x squared minus 3. Right. Number 10 is factoring, but I give you 4 terms. So the classic approach when I ask you to factorize a 4-term polynomial is factor by grouping. What you do is you sort of separate the problem to 2 bits. The first 2 terms is its own group, and then the last 2 terms is its own group. And do notice that I highlighted the middle symbol in the second group. You always want to include that middle symbol. So when I rewrite this, when I group them, 4n cubed plus 14n squared, I always put a plus symbol, parentheses, and then I always include the middle symbol, 2n plus 7. So this plus sign here is always there, and this plus sign went over here. So just keep that in mind. And then the idea is to factor out the greatest common factor. In the first set of parentheses, I can factor 2n squared. It gives me a 2n plus 7 left over. And in the second parentheses, there's nothing I can factor. There's no common factors between 2n and a 7. So if there's nothing else you can factor out, you can always factor out a 1, because factoring out a 1 does not change things. Your ultimate goal is to get these parentheses the same, which they are. And because they're the same, we can factor it out in front. And then in your second parentheses will always be the leftovers. And what's left over, we can see, is a 2n squared and a plus 1. So that goes here. And that is the factored form of that cubic. Number 11 is a multiplying rational expressions problem. Number 12 was a dividing one. And the thing I said in the lesson is, it's sort of ironic. When it comes to multiplying and dividing rational expressions, you actually don't multiply and divide. The idea is to factor everything and cancel. Now, this particular problem was actually easy for us because I didn't notice this. The computer program made the question. You notice how this numerator is 100% the same as this denominator. So I can actually skip the factoring part for those pieces and just go ahead and cross them all out because they're 100% the same. So this problem was actually super duper easy to begin with. So then all I'm left with is a 1 over 4p minus 8 times 2p squared plus 2p minus 12 over 1. So now all I need to do is just factorize this piece and factorize that piece. So that equals 1 over. So for the first denominator, it's just a binomial, so just regular GCF. I can pull out a 4, leaving me a p minus 2 behind. And then in the second numerator, they all have a 2 in common, so I can pull out a 2, p squared plus p minus 6. And then in my next step, this is a quadratic trinomial. I can go ahead and factorize him. 1 over 4p minus 2 times 2. And then you just factor him like normal. So that's p and p plus 3 minus 2. And then you go ahead and cancel out what's in common. The p minus 2's will cancel. I can reduce the 2 and the 4. So this 2 is completely gone. And when I divide this 4 by 2, I get 2 left over. And then all that you have to do is just, quote, multiply straight across. But if you want to leave it in factored form, you may. So the only thing that's left over in the numerator is the p plus 3. And the only thing that's left over in the denominator is a 2. Number 12 should be the same idea, except it's division. Well, remember that whenever you divide by a fraction, you got to multiply by the reciprocal. So before you begin, you're just going to rewrite the dividend, the first fraction, change the division into multiplication, and then take the reciprocal of the second fraction. Now it's a multiplication problem. It's the same two ideas. You factor and cancel. So there's only three pieces we need to factorize. This piece, and this piece. So the 4 just stays as the 4. 5x squared minus 2x minus 3. So I'm not going to spend time explaining. I'm just going to go straight to the answer. So what's that? That could be 5 and 1. So it's going to be a minus 1 plus 3 here. That'll give me a negative 2. Yep. And over here, 25 could be 25 and 1 or 5 and 5. I think it's going to be 5 and 5 because the numbers are so close together. So let's see here. 6 is 1 and 6. 2 and 3. I can do 15 and 10. Oh, there we go. Plus 3 and plus 2. And in the denominator here, 5x and x. 4 and 1, 2 and 2. It's 2 and 2. Plus 2. Plus 2. Again, I went through that fairly quickly, but all I was doing is guessing and checking. And then all you got to do is cancel out the common factors. The 5 plus 3's cancels. 5 plus 2 cancels. And that's it. That's all that cancels. Now again, for me at least, you actually don't have to multiply. You can leave in factored form. So the only thing that's left over in the numerator on top is a 4. And the only thing that's left over in the denominator is the x minus 1 and the x plus 2. And you don't need to FOIL it out if you don't want to. That is a perfectly acceptable answer. Number 13 was simplifying a complex fraction, and there are a lot of techniques to do this, but the technique I like is clearing the fraction. So that's the solution I'm going to show. To clear the fraction, you need to find the LCD of the inner denominator. So you got to find the LCD of the denominators within the fraction. If you don't know how to do this, or if you forgot, what I like to do is to write down the denominators right on top of each other. And what I want to do is factorize them as much as possible. For regular numbers, you want to prime factorize them. 2 is already a prime number. For polynomials or variable expressions, you want to factorize them like normal. It's x plus 4, there's not much I can do with them, so I'm going to leave it as x plus 4. Notice I left it in parentheses because the x and the 4 belong to each other. And then this 2 here, and then this x is by itself. So LCD equals, you always start with what's common, and what you're supposed to do is look up and down the list, not left to right. Hopefully you guys can see there's only one common factor, the 2's here. So there's definitely a 2 in the LCD. Now there's a reason why I put the parentheses around the x plus 4, because this guy here is one single package. I cannot say that these x's are the same. That's a false statement. Because the plus 4 is attached to the x. So 2 is the only thing that's in common. So my LCD, I need to put down the leftovers. This x is left over, I need to put him down. This x plus 4 is left over, I need to put him down. So that's the LCD of this problem. What you want to do then, once you find the LCD, is multiply every single term by the LCD. So what I'm going to do is I'm going to rewrite the problem, but give myself some space. X plus 2 space plus 4x over x plus 4 all over 1/2 space minus 2 over x. That way it gives me room so I can multiply the LCD. So 2x, x plus 4, 2x, x plus 4, 2x, x plus 4, 2x, x plus 4. Now because we're using the LCD, if we're doing it correctly, all of the mini denominators should cancel out. So on the top left, the 2's cancel out. Top right, the x plus 4's cancel out. Bottom left, the 2's cancel out. The bottom right, the x's cancel out. And all that's left to do is multiply, distribute what's left over. So in the top left, I have an x times x, which is x squared, and I'm going to multiply the x squared into the x plus 4. So that's x cubed plus 4x squares. In the top right, I have 4x times 2x, which is plus 8x squared. All over, in the denominator, I just have x times x plus 4, which is x squared plus 4x. And in the denominator, I have 2 times 2, which is 4, and I'm going to distribute the 4 into the x and the plus 4. Do note, however, that we're subtracting this fraction. So instead of thinking of it as 4 times x plus 4, you should be thinking of it as negative 4 times x plus 4, which gives us negative 4x minus 16. Then all that's left to do is to combine like terms and simplify. So in the numerator, we have like terms here. In the denominator, we have like terms there. So the numerator is just an x cubed plus 12x squared. In the denominator, those x's cancel out, so all we have is x squared minus 16. You could factor some more, but nothing cancels out, so that is the simplified form. Number 14 was just linear equation. Again, with all these problems, multiple ways to do it. This is the thing that sticks out to me. First thing I notice when I'm solving equations in general is I notice parentheses and numbers in front of them, so that usually tells you to distribute. So that gives us negative 30 plus 6n plus 5 equals 8n plus 14 minus 5n. Notice anything that I did not highlight, I just copied down. Next, I'm going to combine like terms on each separate side. So I have the negative 30 with the 5 here, and I have the 8n with the negative 5n here. They're like terms. So on the left gives me 6n minus 25, and on the right I have a 3n plus 14. Now it's a simple linear equation. The idea is you want all the variables on one side, all the constants on the other. Hopefully we can do two steps at once. I'm going to subtract the 3n from both sides, and then I'm going to add the 25 on the other. I'm moving the variables to the left, moving the regular numbers to the right. This gives us 3n equals, these guys are gone, these guys are gone. What's that, 39, and then divide both sides by 3, gives you a 13. Number 15 was an example of an absolute value equation, and the idea was that before we do any special techniques or tricks, you have to get the absolute value symbols by itself. I hope that highlights them, that by highlighting it, I hope that makes it clear that we need to get rid of the 8 and the 9. So get rid of the thing that's farthest away first. To get rid of the 8, I'm going to subtract 8 from both sides. 9 absolute value, negative 5 minus n equals, what's that, 54. And then divide both sides by 9, gives you negative 5 minus n is equal to 6. Now, the way we deal with the absolute value is to apply the definition. Recall that absolute value of anything, x, will always give you one of two things. The identical thing you put in, or the exact opposite of you put in. Which one you get depends on the input. You get the identical thing out if what you put in was positive, and you get the exact opposite thing out if what you put in was negative. Since this thing in the equation inside the absolute value contains a variable, we don't know if that guy is positive or negative. So as problem solvers, we have to cover both bets. That means this absolute value expression, by definition, could give me the identical thing right back out, negative 5 minus n, which, according to the equation, equals 6. However, by definition, it could also give me the exact opposite. So to do opposite, you just slap on a negative in front, which at the same time equals 6. Now it gives you two smaller equations to solve. Let's focus on the left equation. We're going to add 5 to both sides. Negative n equals 11. Divide both sides by negative. You get n equals negative 11. On the right equation, you can go ahead and distribute the negative in, or what I like to do is I like to divide out a negative 1. That way all of my solving steps will be the same as the other equation. Go ahead and solve for n. You add 5. And then divide out the negative, so n equals 1. Now notice what our equation was before we applied the definition, that line there. It was an absolute value equaling a positive number. Technically, a good problem solver, a good mathematician will always check his answers, but if you just have a regular number on the other side, as long as you trust your arithmetic, as long as you trust your math, whatever answer you get is the answers that you should have. So I'm not going to bother plugging them in. I trust my math. Negative 11 and 1 should be the answers. If there were variables on both sides, I would check my answers. Number 16 was just a standard quadratic equation. I tried to give you a hint there. The instructions originally said solve by factoring, but honestly, if you use completing the square quadratic formula, I didn't care what method you use, as long as you just solved it. But the idea to solve a quadratic is to get everything on one side. You want 0 on one side. Since I like the square to be positive, I'm going to move everything to the left. So I'm going to add 8n squared over, giving me 7n squared equals 6n plus 1. And then I'm going to subtract both the 6n and the 1 to give me 7n squared minus 6n minus 1 equals 0. And the idea is you try to factor it. And if it's not factorable, use completing the square or quadratic formula. But I think I told you that this was factorable. So 7n and n minus 1 on the right plus 1 on the left. The reason why we want to factorize it is because we can use the zero product property, which says if you have a multiplication problem, this guy times this guy, and it equals 0, that means each individual factor will equal 0. And then you can just solve these linear equations. N equals negative 1/7, n equals 1. Those are your two answers. Number 17 was a rational equation, fractional equation. And again, there's lots of different ways to solve these. I like clearing the fraction. So to clear the fraction, I need the LCD, which means I need to look at all of the denominators. So I'm going to write them stacked on top of each other and factor them. Can't do anything with the x. X squared is x times x. Can't do anything with the x. LCD equals, look up and down for common factors. You have one x in common between all of them. And then the 2 and the x are leftovers. So the LCD is 2x squared. So what I'm going to do is rewrite the equation with some space, because I'm going to multiply. Space equals 3 over 2x squares, space, plus x minus 3 over x. And then just multiply every term by the LCD. Multiplies by 2x squares, multiply by 2x squares, multiply by 2x squares. Let's separate the scratch work here. If we played our cards right, all the denominators should cancel out. This x will cancel out with one of the x's, so the exponent's gone. In the middle, everything cancels out. And on the right side, this x should cancel out with one of the x's. So then you just go ahead and distribute and multiply what's left over. So I'm going to distribute this 2x left over, giving us 2x squares minus 4x equals, there's only a 3 left over, plus, and I'm going to distribute this 2x in, giving you, 2x squares minus 6x. Now, fortunately for us, I hope we can see that if you subtract 2x from both sides, 2x squares, excuse me, that they all cancel out. So it looked like a quadratic, but it ends up being a rather nice linear equation. So get all the x's on one side, get all the numbers on the other, solve, yada, yada, yada. 6x, 6x, 2x equals 3, divide out the 2, x equals 3 halves. Now the one thing with rational equation is it's not an option. You must check your answers. But you only need to check against the denominators, because in math, we can never divide by 0. So let's take a look at our denominators again. In this problem, our denominators were x, 2x squares, and x. And what you want to do is put your potential answers into the denominators. If it makes any of the denominators equal to 0, you have to throw them away. But if I plug in a 3 halves into any of the denominator, I don't get 0, which means our answer is good. So 3 halves is a good answer. Last but not least, number 18 was a radical equation. Just like with absolute values, anytime you have an equation with special symbols, parentheses, radicals, absolute values, and your variables inside of it, the technique is sort of to isolate that special symbol. So before I can do anything, I want to get that radical by itself. So I hope it makes it clear that I need to move the negative k. So to get rid of the minus k, you're going to add k to both sides to give us 4 plus k equals the square root of 6k plus 15. And the idea is simple. Do the opposite. The opposite of a square root is a square. So at this stage, I need to square both sides. And please, 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 when you're squaring a binomial, do not distribute the 2. I see this a lot. This is wrong. We can't distribute the 2 because the plus sign screws things over. It's not properties of exponents. Squaring something, squaring a binomial, you can either use the pattern or just write him out twice and FOIL like normal, right? So that's going to be a 16 plus 8k plus k squared. So that's what's going to be on the left-hand side of our original problem. So this guy here is this guy there. So we have 16 plus 8k plus k squared equals, and then on the right-hand side, the square root and the square will cancel, giving you just a regular 6k plus 15. And then you just solve it like a regular quadratic. Let's go ahead and subtract 6k, or move everything onto one side. And then let's do 2 steps at once and minus the 15 here. So that's going to give us, I'm going to write the k squared first, and then 8k minus 6k is positive 2k, 16 minus 15 is a positive 1, and solve by factoring, completing the square, quadratic formula, what have you. Fortunately, this guy is factorable, k plus 1, k plus 1. And then either way, you get k equals 1. Now, take a look at the original problem when the radical was isolated. So this line here without the parentheses squared. Notice we have variables on both sides. Technically, we need to check our answers. Not technically, you must. I'm making a mandate. So I want to check k equals 1, and you just plug into the equation before you squared both sides. So I'm going to plug it into the 4 plus k equals radical 6k plus 15. That's what you plug it into. So change all the k's to a 1. You get 5 equals the square root of, let's see, 6 plus 15. Oh, it's not. That's why it's not working. Sorry, guys. Mistake. Back here, that should be k equals negative 1. So our answer is actually negative 1. Let's check k equals negative 1. So that gives us a 3, and a negative 6 plus 15 is a 9. And of course, 3 equals 3. So negative 1 is a good solution.